Hello, and welcome to this Patton webinar. My name is Katie Paris, your host from IHS Global Spec. I would like to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Patton Presentation in the upper left is the primary window for today's webinar. You should be seeing the welcome slide there right now. Just to the right of the main presentation window is the Speaker Bios window with background information on today's presenters, Nathan Meyer, Johnny Grant, Ed Whitman, and Sean Garrity. Just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the Q&A window and click Submit. Your question will be placed in the queue for the speakers to address when we get to the Q&A session. At the bottom of your screen, you will see 7 buttons. The first 3 either minimize or restore the 3 windows we've already talked about. The others allow you to share this webinar with a colleague, complete a survey, and lastly, do a little troubleshooting like running the system test or consulting the FAQ document. The button second from the right is the volume control button for the webinar. If you can't remember what a particular button does, just hover your mouse pointer over it and a tooltip will appear with a description of the button's function. Now let me introduce today's speakers. Nathan Meyer is the Field Applications Engineer with Patton. With decades of experience in the networking field, Mr. Meyer specializes in product specification and design with expertise in detailed networking protocol operations and systems troubleshooting. Nathan holds a BS from the University of Minnesota and an MS from Johns Hopkins University. Next, we have Johnny Grant III. He is a product line manager. Mr. Grant has over a decade of experience as a product line manager for Patton Electronics. He is responsible for identifying market requirements and defining product solutions that address true customer needs. Also with us today is Ed Whitman. He is the Computer Network Specialist Lead for the Maryland State Highway Administration. Ed has over 20-plus years in the computer industries, starting first in the private sector. Ed has been a technical lead on several major state projects from his time working with the MDE to now spending his time working with the Maryland State Highway Administration. And finally, we have Sean Garrity. As a leader of Patton's North American sales operations, Mr. Garrity will present current opportunities to leverage relevant Patton products cost-effectively in the real world. Today's talk will focus on Multi-Drop Ethernet, MDE. Today we will learn about what Multi-Drop Ethernet is. We will explore the short history and likely future of MDE technology. We will learn the pros and cons of MDE versus EtherCAT, Fieldbus, and other alternatives for industrial networks. And we will discover real-world scenarios in which MED has been successfully implemented. Now that's enough of me. Let's get this webinar started with our first presenter, Nathan Meyer. Nathan, the floor is yours.
Thank you, Katie. Just to introduce myself, I'm Nathan Meyer, a Field Applications Engineer for the Americas at Patton Electronics. In my portion of the webinar, I'll discuss Ethernet in the context of MDE, that is multi-drop Ethernet. It will include what MDE is, its topologies, the migration from legacy serial deployment to industrial Ethernet, issues with proprietary Ethernet, and finally, the advantages in using MDE devices. MDE simply means multi-drop Ethernet. To understand it more clearly, let's review the evolution of Ethernet. The original Ethernet standard was based on a coaxial bus topology in which multiple stations were dropped at various points along the length of the cable. They were 10-base-2 and 10-base-5, also known as thick Ethernet and thin Ethernet, respectively. Data transmission was half duplex mode and operated in CSMA/CD mode. Carrier sense multiple access with collision detection. In other words, multiple devices could access the same medium, but only when it sensed that no other devices were transmitting. Because collisions could occur, retransmissions would be necessary, but not necessarily successful. Ethernet is therefore a non-deterministic protocol, which means there's no guarantee that the transmission would be successful. Deterministic protocols guarantee successful transmission. The successors, 10 base T and 100 base T, used two twisted pair cables that connected in a point-to-point manner and could support full duplex transmission. In addition, collisions became a minor concern once the 10 or 100 base T implementation used switches instead of hubs. 100 base T is also known as fast Ethernet, which will be our principal reference. To sum up these two media types, coaxial Ethernet was half duplex, multi-drop, and collision sensitive, whereas fast Ethernet is point-to-point, full duplex, and collisions infrequent. Now to MDE, multi-drop Ethernet. MDE technology offers a combination of features from the coaxial version of Ethernet and also the twisted pair version. MDE Ethernet extenders use a single twisted pair to transport full duplex fast Ethernet. Extenders at the endpoints terminate the single twisted pair transmission line, but the intermediate devices, the MDE extenders, function as repeaters while simultaneously dropping one or more ports for Ethernet access. Multiple MDE units may be connected in a daisy chain style so that the MDE technology can connect multiple stations, reminiscent of thick and thin Ethernet. However, it supports full duplex transmission like fast Ethernet with minimal concern for collisions. However, the coaxial, twisted pair, and MDE versions of Ethernet are still considered as a non-deterministic protocol. Later, we will see that some industrial protocol stacks, while operating over the standard Ethernet frames and physical layer, added capabilities by using various means to provide deterministic behavior in a non-deterministic network. MDE topologies. In the previous slide, I mentioned the topologies supported by the thick and thin Ethernet, twisted pair Ethernet, and alluded to the MDE topology. Let me explain the topologies in slightly more detail. In this slide, the blue lines are the single twisted pair transmission line between Ethernet extenders, and the red lines and red symbols indicate Ethernet port connections. Standard fast Ethernet operates in a point-to-point topology. Ethernet can be extended beyond the 100-meter maximum segment length by using Ethernet extenders. They transport full duplex Ethernet traffic over a single twisted pair between the two endpoints, hence point-to-point. In the multi-drop configuration, we add one or more MDE Ethernet extender units. The MDEs function as repeaters with ports to connect to Ethernet devices at the intermediate points. Using multiple repeaters extends the overall end-to-end length of the network and also drop Ethernet ports at the intermediate locations. We can build the star topology by connecting endpoint Ethernet extenders to the MDE devices' Ethernet ports. The diagram implies but does not show the extension of more Ethernet extender units. By using endpoint and MDE-style Ethernet extenders, a broad variety of networks can be addressed by your application. Alternatives: migrating RS-485 to Ethernet. The legacy alternative for industrial networks is the use of serial interfaces at the physical layer, such as RS-485 and RS-232. Industrial applications include process control systems, real-time fast motion control, PLCs, sensors, I/O modules, safety controls, and others. Here's an example application from the energy industry. The energy industry, whether an oil, gas, wind turbine, or other energy field, needs to measure the flow of oil, gas, generated electricity from its source to the transmission pipes. The building at number 3 is the central location for communicating with flow computers located at each derrick. From this central location, the operator can calibrate, program, or configure the flow meter, request a data dump, or execute other operations. The flow computers in the application diagram have either an RS-232 or RS-485 electrical interface that operates at a maximum data rate of 19.2 or 38.4 kilobits per second. The SCADA server uses RS-232 interfaces that connect to modems, making links to the derricks. The point-to-point connection, circle number 2, has a modem at each end of the link, one at the flow computer, the other at the SCADA server. With multi-point connections, one modem or interface converter connects to the SCADA server to communicate with the flow computers, circles number 1, over a single twisted pair. Each flow computer has its own modem that connects to the SCADA server's central modem. The SCADA system uses the Modbus communication protocol as a layer 2 protocol over the serial link. Other communication protocols may be selected. So the next slide is migrating RS-485 to Ethernet, and how can we migrate from the legacy deployment to Ethernet. The following scenarios show the migration can be cost-effective and technically easy. Scenario number 1, RS-232 or RS-485 based flow computers are already deployed. The SCADA server is converted from RS-232 or RS-485 ports to Ethernet ports. The installation of Ethernet extenders use the existing 2-wire twisted pair infrastructure or migrating to an Ethernet-based system. There's no need to replace the serial-based flow computers by using the low-cost terminal servers. The terminal servers turn the serial RS-232 or RS-485 port into an Ethernet port. Scenario number 2 is deploying new communication links using Ethernet communications. In this case, select the flow computer with the Ethernet interface. The installation of the communication link is very simple. Install a pair of Ethernet extenders over a single twisted pair infrastructure. Instead of deploying individual point-to-point links to each derrick's flow computer, use MDE Ethernet extenders in the daisy chain fashion to reach the most distant derrick while accessing intermediate derricks with the dropped Ethernet connection from each MDE device. Why migrate to Ethernet for industrial applications? The various industrial Ethernet protocol stacks offer higher speed and enhanced capabilities over a standard infrastructure that can be connected into your existing office network. For optimal performance in the industrial networks, it's crucial that the right design decisions are made regarding the best topology, industrial Ethernet protocol, and equipment for the proper environment. Alternatives. Industrial Ethernet protocol stacks. Different industrial Ethernet protocol stacks evolved to address the unique performance in industrial applications. Probably the defining characteristic is real-time. In industrial automation applications, time-critical data is usually transmitted cyclically, implying real-time. Real-time has two main components in the industrial applications. First, a fast response in terms of quick cycle times, and secondly, a low jitter, which is the variation between cycle times. In hard real-time applications, the cycle and jitter times are most demanding to achieve suitable synchronization. Typically, the most demanding real-time applications use a proprietary protocol stack. The goal in designing the non-standard Ethernet is to create deterministic behavior in an inherently non-deterministic protocol. The protocols on the right side stack include EtherCAT, PowerLink, Circus 3, and Profinet IRT. Some of the protocols on the left-hand side stack use IEEE 1588 for meeting the demands in hard real-time applications. The protocols, Modbus TCP, EIP, which is Ethernet IP, and the IP stands for Industrial Protocol, Profinet IO, and Profinet RT, can operate over standard Ethernet networks, although good design practices would create multiple collision domains for optimal performance. The non-standard Ethernet protocol stacks would need a gateway or router for connecting to the office network. Proprietary Ethernet and Ethernet extenders. Whether we can use standard Ethernet switches and Ethernet extenders depends on the real-time requirements of the industrial network. Profinet, for example, is seen on both standard and proprietary protocol stacks. Profinet is designed to be used in a broad range of real-time applications. Motion control is the most demanding, with cycle times as low as 31.25 microseconds. Factory automation has a cycle time around 10 milliseconds, and process automation can operate at even higher cycle times, perhaps more than 100 milliseconds. Profinet IO, used in process automation, can use any simple unmanaged switch. It is similar to normal IT communication networks. Profit RT, common in factory automation, is more demanding, requiring the use of 802.1q VLAN and prioritization. Will operate with a standard switch, but typically only managed switches respond to prioritization. Profinet IRT, isochronous real-time, is for the hard real-time applications and must use specifically designed switches. Patton's Ethernet extenders will function in Profit IO and Profit RT, but not Profinet IRT. In general, the type of switch is dependent on the level of determinism, meaning the demands of the real-time requirements. MDE advantages. MDE using Patton Ethernet extenders offers numerous advantages in industrial Ethernet applications. Firstly, Ethernet is the lingua franca in the networking world. That is, it is the networking protocol language spoken around the world. By selecting key features from coaxial and fast Ethernet, we can do multi-drop Ethernet over full duplex connections and not just point-to-point links. In addition to dropping an Ethernet port at an intermediate point, the MDE Ethernet extender can operate solely as a repeater to extend the maximum distance. Using MDE as a repeater or to drop an Ethernet port, it far exceeds the 100-meter maximum segment length. Some industrial Ethernet protocols require VLAN support. The MDE devices are able to handle the larger Ethernet frame size when VLAN tagging is used. The MDE also does transparent bridging, so local traffic remains local and only traffic destined to another point is forwarded. Finally, the MDE extenders operate in an extended operating temperature environment from -40 to +185 degrees Fahrenheit. Installation options for DIN rail or wall mounting provide needed flexibility desired in industrial environments. This concludes my brief presentation on MDE technology in industrial networks. Katie, thank you very much for this opportunity.
Nathan, thanks so much for talking with us today. Stick around because I am sure there will be some questions for you at the end of today's webinar. The next presenter up is Johnny Grant. Johnny?
Hey, thanks, Katie. As introduced, my name is Johnny Grant, and I'm the product manager for Patton's connectivity portfolio. My best performing product line is these CopperLink Ethernet extenders we are talking about today. Our Ethernet extenders offer three primary benefits. The first is explained in the name. We are able to extend Ethernet well beyond its distance limits. In some cases, we are pushing standard Ethernet up to 6 miles. The second and equally important benefit is that these products enable our customers to reuse their existing infrastructure, including older infrastructure. Mostly, this is telephone-grade copper wires but we also support coax. This infrastructure was often previously used for telephones, lease lines, alarm circuits, RS-232, 422, 485 circuits, T1, E1, and the like. And finally, as Nathan has discussed, the MDE Ethernet extenders support topologies and environments not supported by most commercial or office-grade networking gear. Nathan has gone over the meaning of MDE, topologies, and various different standards used in industrial Ethernet applications. I would like to take the opportunity now to focus on a few of the myriad of customer use cases we see. Let's start with a few elevator stories. When I say elevator story, I really mean elevators. Our first customer application shown here is an example of elevator control, where the extenders are used in point-to-point mode or point-to-point topology. Like most of the industrial world today, elevator manufacturers are converting their controls from native serial to native Ethernet. Sounds easy, but it can be a real problem and expense for the customer. So customers are turning to Patton daily. We, along with the elevator manufacturer and integrator, really are helping customers save money by avoiding the requirements to install new infrastructure. That is to say, upgrading to fiber or Cat5 Plus cabling. In this application, the customer has complete control of their elevator systems via Ethernet. And to add value, they are now able to add to the install an IP camera for surveillance, IP phone for emergency calls, an elevator LCD to run various different advertising and announcements. This is all over the same single twisted pair previously running RS-45 that was used for control only. So not only did the CopperLink solution allow for Ethernet connectivity, it offered a significantly higher bandwidth, close to 100 megs, over its low-speed RS-485 predecessor. Here is an example of an elevator application that was a little more specialized to the unique multi-drop features of our product. This elevator control system originally used RS-45 multi-drop over a single twisted pair, reaching up to 250 floors of a high-rise building. Each floor has its own control box and connects to the twisted pair in the riser. When this elevator manufacturer released the current generation of control units, they eliminated the RS-45 interfaces in favor of the newer standard Ethernet. This application, unlike the first elevator story, does not require lots of bandwidth. The customer just needed access to the elevator controls via Ethernet over older and multi-dropped wires. Using a CopperLink MD in place of the original RS-45 modems allows for this transition from serial to Ethernet without having a single change to the physical infrastructure, saving the customer time and money. For industrial manufacturing environments, Ethernet initially began at the management and control levels of a production plant. However, industrial Ethernet really has crossed the chasm and has now penetrated all the way down to most industrial devices. PLCs, sensors, weighing mechanisms, and other I/O devices are more readily available today with Ethernet ports. In manufacturing environments, we are also seeing the need to support longer distances and higher speeds due to real-time considerations Nathan discussed earlier today. The backbone of the Czech Railways network includes both fiber and multiple copper pairs. The Czech Railways deploys CopperLink Ethernet extenders to extend coverage to station areas with low populations. While fiber does offer unmatched rate and reach, the cost to run fiber to these remote stations is not considered cost-effective. Ethernet extenders line rates decrease as the distance increases. Simple physics. In order to keep the desired bandwidth, the Czech Railways deploys the CL1314 MDE to act as repeaters, regenerating the signal at each hop, maintaining solid bandwidth to each one of those locations. Both Patton and I are privileged today to be accompanied by one of our local customers taking advantage of the CopperLink MDE solution. Mr. Ed Whitman of the Maryland State Highway Administration. I will now hand over the floor to Mr. Ed Whitman to talk about how the Maryland State Highway Administration is using our CopperLink MDE solution for next generation traffic control applications. Thank you.
Thanks, Johnny. In order to meet traffic monitoring requirements issued by Maryland's governor, the Maryland State Highway Administration, SHA, would have to monitorize their traffic control system, transitioning from a closed-loop architecture to essentially manage IP network. We need a cost-effective solution that could be implemented quickly within our limited budget. The old closed-loop system interconnected regional traffic signals using leaf-line modems. The low data rate modems operated over copper twisted pair cabling infrastructure, installed and working for years. The new system will leverage modern IP technology and is designed to keep traffic moving at the optimized rate, in addition to monitoring the traffic. The traffic monitoring setup employs two primary sensors. One, video mounted on traffic light structures, and two, sensors installed under the roadway halfway between intersections. The video camera determines if any traffic is waiting at an intersection. The sensor senses the traffic rate of flow. The sensors transmit their information to a control box located at the intersection, which then adjusts the traffic signal timing according to a live condition. To monitor and control the system, engineers can access not only the control box, but each individual device over the IP network from SHA. The greatest challenge to IP enabling a legacy system over involving cabling issues with the distance limitations of standard Ethernet. Even though Ethernet technology serves the backbone of IP connectivity today, the standard is limited to a maximum reach of over just 400 feet per network segment when operating over Cat5 or greater cable. Fiber optic cabling can be used to resolve the distance limitation, yet installing it is costly and cumbersome. In this instance, it would cause major delays with road closings, demolitions, cable runs, and reconstruction. WiMAX, a modern alternative for the IP transport, is subject to electromagnetic interference, bandwidth instability, in addition to reliability and security concerns. Because of such challenges, the way forward was looking pretty murky. I discovered a local manufacturer here in Maryland, Patton Electronics. Patton offers network devices that enable Ethernet to operate over single twisted pair cabling across distances of more than 3 miles. By reusing our existing copper network, the project could be completed much faster and at a lower cost than anyone had imagined. After discussing the topology and their unique highway network with Patton, I was introduced to their CopperLink MDE Ethernet extender. It was an integrated 4-port Ethernet switch, allowing me to interconnect IP-enabled cameras, controllers, and sensors with an IP router installed in the equipment cabinet in one of our main central intersections. The MDE has 2 LAN ports that interconnect neighboring intersections over our existing copper infrastructure. At the last hop, we would use Patton's ruggedized long-range CL1340R to terminate the final Ethernet segment operating over the legacy copper cable. With the MDE installed at each central intersection, our old closed-loop system is now IP-enabled, interconnecting all traffic signals, cameras, and sensors and controllers. The entire system can be managed remotely over the administrator's IP network from SHA or headquarters. In conclusion, I was looking for a company that could be reliable with a good resource and that could help me in my dilemma with connecting these copper signals together. I found that Patton had the right device. They were willing to come out and help me engineer or help me design what I needed, which they did, and I have had these things installed for several months and with no issues. So we are looking forward to continuing using Patton for more of our traffic signals coming up and through all the state of Maryland that needs to be put online.
Johnny and Ed, thank you so much for your informative part of the presentation. Our final presenter of today is Sean Garrity. Sean, take it away.
Katie, thank you for the introduction. I want to thank everybody for joining us today on this webinar. I hope you found the topic very useful. I'd like to go over a little bit of Patton's history and give you a brief introduction not only to our organization, but I think an exciting offer that we all can take advantage of on this topic from today's webinar. Patton is a family-owned company. Everything Patton designs and manufactures is from our own source technology. We make everything in our factory here in the United States, right outside of Washington, D.C., which really gives us a very different feel from most manufacturers in today's environment, still being U.S.-based, not only from technology but also manufacturing. We have unrivaled customer support, meaning all of our products have free customer support with them for the life of their products. These are actual human beings you can call, which really separates us from our competitors in the marketplace. And additionally, Patton has offices throughout the world to support people both globally and locally for their projects and services. We have a very robust product line running from device servers all the way through WAN aggregation, covering things along the lines as bandwidth on demand, voice over IP, surge protection, and of course, our multi-drop Ethernet solutions that we're talking about today. And Patton makes it very easy for people to get in contact with our channels and representatives throughout the world. From our home page, people will see right on our top banner, How to Buy link. Once we access this How to Buy link, it'll open up a page that'll bring you to either having Patton contact you directly or having us reach you out with one of our local representatives, or to put you directly in contact with one of our regional offices. This way, you will be able to be supported in your own native tongue, your own time, and when you are ready to address your requirements. And part of that offer that we'd like to extend to people on this webinar today is
Patton is combining our CL1314 Ethernet Extender 2-pack at your normal channel price, and you'll receive our CL1314 multi-drop Ethernet Extender for free. We're really hoping this entices the community to go out and try this solution, and we look forward to you contacting us with your applications and any details we can help you with.
Katie, thank you for your time this afternoon.
Thanks, Sean, and thanks to Nathan, Johnny, and Ed. Now it is time for our question and answer period. If we don't get to your question, don't worry. We will have an answer for you within 24 hours. The complete Q&A transcript, including answers we did not have time for, will be sent to all of our registered attendees and will be posted with the webinar when it goes into on-demand mode. Now on to our first question. Ed, it looks like the first two questions are for you. Both of these questions are referring to the Maryland State Highways installation of the CopperLink MD solution. Ed, how did the installation go?
With the help with some of the Patton engineers that came out, the installation went seamlessly. I mean, it was easy to set up. The data flow was exactly more than we expected, and everything worked great, and we're looking forward to a good relationship.
And a follow-up to that, how is your setup working now?
The setup is working great. We check it daily to see how the signals are talking to each other, and we have not had one issue. We have getting no data loss, no drops signals. So right now, even with some of the heat that we have had over the summer, and we have not had one issue with any of your devices.
Thanks so much, Ed. The next question looks like it's for Nathan. Nathan, this attendee would like to know, what is the difference between deterministic and non-deterministic networks?
Yeah, thank you, Katie. It's a good question that many people don't understand the answer to. So, Token Ring is a deterministic network because it guarantees the delivery of the data packet. Standard Ethernet, being non-deterministic by design, does not guarantee delivery. We all know that if a standard Ethernet link reaches 80% traffic, the chance for collisions rises exponentially. The industrial protocols have modified in various ways to create deterministic network behavior in an inherently non-deterministic network. The reason is to meet the requirements of real-time industrial applications. Thank you.
Nathan, here's another one for you. What is IEEE 1588?
Okay. IEEE 1588, Katie, is also known as the Precision Time Protocol. This protocol is used to synchronize clocks in a network that requires more precision than NTP or GPS, and therefore is suitable for measurement and control systems requiring clock accuracy in the sub-microsecond range. IEEE 1588 is often employed in protocols in the standard, as opposed to non-standard, Ethernet protocol stack. Non-standard Ethernet protocols use techniques such as time slot reservation.
Thanks, Nathan. This one is also for you. How do you view the future of MDE technology?
Well, Katie, one hint is the protocol CC-Link-IE, because it is based exclusively on gigabit Ethernet. But the other interesting thing to watch is the intense competition between the supporters of the different protocols. The strongest protocol competitors are attempting to be applicable in the broadest range of industrial applications, from process control to factory automation to the highly demanding motion control. For example, Circus 3 has a highly deterministic motion protocol, whereas EIP is stabilized with IEEE 1588. So whatever the fallout may be, there will be a future for MDE technology because of its ability to extend Ethernet distance and also to provide a multi-drop in full duplex mode. Thanks, Katie.
Thanks, Nathan. Johnny, this next one is for you. Can you manage the MDE devices?
Well, Katie, I guess the simple answer is yes. You can configure the devices through the Ethernet port, the same Ethernet port used for data. Really, the configurations you're going to do are within the local unit. The local unit will then send the commands over to the remote unit. Most typically, you're only adjusting the line rate to best suit the application. But truthfully, we designed the CopperLink product. One of the goals of our CopperLink product is our customers can use them straight out of the box. So really, it's just plugging them in, powering them up, and playing what we call plug and play.
Thanks, Johnny. Nathan, back to you. Is MDE a field bus technology?
Very good question. No, it is not a field bus technology. Rather, it is an Ethernet extension technology with additional capabilities. With Ethernet extension, you connect to any standard copper version of Ethernet in order to go beyond the 100-meter maximum segment distance.
Thank you, Nathan. Johnny, here's another one for you. Is the MDE technology a layer 2 or layer 3 device?
Well, Katie, it is a layer 2 device, and the MDE really functions as a switch. Therefore, much simpler to configure than a layer 3 device or router. One of our goals in releasing CopperLink products is that they're plug and play and very simple to configure.
Thanks, Johnny. We do have time for a couple more. Johnny, here's another one for you. What is the maximum data rate and distance of the Patton MDE Ethernet extender?
Well, for the CopperLink 1314 2-pack at 5.7 megs, we are looking at distances of about 9,000 feet, or just a bit under 3 kilometers. At the lowest supported rate, 192 kilobits per second, we're looking at 4.25 miles, or about 7 kilometers. Now, as described in the CheckROA's application earlier, a CL1314 multi-drop Ethernet extender can be placed in between the standard CopperLink 1314 2-packs, doubling the distance to 3.5, or I believe it's about 5.5 kilometers. At 192 kilobits, we can extend your Ethernet connectivity to 8.5 miles, or close to 14 kilometers. Now, another MDE can be added to triple the distance. Hopefully that answers the question.
Thanks, Johnny. Nathan, this last one is for you. This attendee says, I'm confused about real time. You described it as different types of real time. Can you explain that again?
Yes, I certainly can, Katie. The different types of real time depend on the cycle time and the jitter between each cycle. Some applications are very forgiving, and even though are still real time, they don't require as demanding precision in the clock. On the other hand, the hard real-time applications have motion control and need to synchronize the movement, for example, of many different axes of a robot. Consequently, the synchronization requirements are much more demanding. So the accuracy of real-time depends on the industrial application. Thanks very much, Katie.
All right, everyone, we're going to have to wrap up this webinar right there. I want to thank all of our speakers, Nathan Meyer, Johnny Grant, Ed Whitman, and Sean Garrity for spending some time with all of us today. And thank you to all of our audience members for being a part of this webinar event. To find more information about today's webinar, please feel free to contact any of the Patton speakers, and as always, feel free to call or email us with any questions. You will be receiving an email from us with the link to the on-demand version of this presentation, a PDF of this PowerPoint, an FAQ document, and a Q&A transcript. Again, thank you for taking the time to learn more about multi-drop Ethernet for industrial applications. Take care, and we'll talk to you soon.